How do you know if your embeddings are good? For years, the answer was, run them on the analogy task. King minus man plus woman equals queen. Do 1,000 of those. Report accuracy. Publish. Then in 2016, someone pointed out, the analogy task is a really weird benchmark, and the whole field kind of blinked. Today, how NLP measures word embeddings, analogies, similarity judgments, downstream tasks, and the honest problem, embeddings can pass every benchmark and still be full of racial and gender bias because they're mirrors of the text that trained them. Last video was ELMO, contextual embeddings. 6 state-of-the-art benchmarks fell in one paper, which is a great story. But if you rewound and asked me, which benchmarks? And how do those benchmarks even define good? I glossed over that. Today I'm going to be honest about it, because evaluation in NLP is trickier than the leaderboards suggest. The puzzle for today. You've built a set of word embeddings, Word2Vec, Glove, Elmo, whatever. Someone hands you a competitor's embeddings and says, which is better? How do you answer that? Turns out, there are 2 families of answers, and they don't always agree. Today's 3 beats. First, intrinsic evaluation, analogies, similarity judgments, the Google Dataset, what NLP has been using since 2013. Second, the Linzen 2016 critique, what's weird about the analogy benchmark, and extrinsic evaluation as the honest alternative. Third, the bias problem. Embeddings absorb the gender, racial, and cultural patterns in their training text, which is not fine. And why good embeddings isn't a single question. Beat 1. Intrinsic evaluation. It means test the embeddings on their own, not inside a downstream task. Just directly probe whether they have the properties you want. 2 main flavors. First, the analogy task. Second, similarity judgments. Let me walk both. The analogy task. Mikolov released this alongside Word2Vec in 2013. It's a text file, 19,000 analogies, half syntactic. Big is to bigger, as small is to smaller, half semantic. Athens is to Greece as Berlin is to Germany. For each analogy, subtract the first vector, add the third, look at what word is closest to the result. Score 1 if it matches the 4th word. Total accuracy across 19,000 items. Your embeddings analogy score. The similarity task. There's a dataset called WordSim 353. 353 word pairs. Humans rated each pair for similarity on a 0 to 10 scale. Tiger and cat, high. Car and banana, low. To score your embedding, compute cosine similarity for each pair. Correlate with human ratings. High correlation, good embedding. There's a bunch of these. Simlex 999 men, RG65. Variations on the same idea. Beat 2. Linzen 2016. Paper title, Issues in Evaluating Semantic Spaces Using Word Analogies. Linzen looked at the analogy task and pointed out, the way people score it is weird. When you compute king minus man plus woman, you exclude king and man and woman from the candidate answers, because obviously the closest vector to that arithmetic is often just king itself. If you DONT exclude the input words, accuracy drops to near 0. So the benchmark score depends heavily on an implementation detail. Linzen went further. He showed that a lot of the analogy performance comes from proximity artifacts, not real analogical reasoning. Words that are simply close to your target output in raw embedding space will score high, whether or not the analogy structure is really there. The famous Cayenne minus man plus woman result might be less about geometry capturing gender and more about queen happening to sit near Cayenne, regardless. So what's the alternative? Extrinsic evaluation. Plug your embeddings into a real downstream task, sentiment classification, question answering, named entity recognition, and measure that accuracy. If your embeddings help the model do a real thing, they're good, simple, and honest. But expensive, because now you have to actually build and train real models to test them, which is why intrinsic tests stayed popular for so long. Cheap and fast beats honest and slow. Beat 3. The uncomfortable part. Bolukbasi and colleagues in 2016 pulled a Mikolov-style analogy on Google News Word to VC vectors. Man is to computer programmer as woman is to what? The answer the model gave was homemaker. Doctor was to man as nurse was to woman. Every gender stereotype in the training text showed up in the geometry, not subtly, blatantly, in a benchmark passing embedding. Racial bias too. Names that are more common in Black American communities, associated with negative valence words. Names more common in white communities, associated with positive valence words. Because that's how those words appear in text on the internet. Embeddings are mirrors. If your training data contains bias, your embeddings will too. And when you plug those embeddings into resume screeners, loan applications, or search engines, real people get hurt. So what does good embeddings actually mean? Depends on the task. Analogy accuracy, sure, if that matters to you. Downstream classification accuracy, sure, if you're building a classifier. Fair, unbiased vector geometry. Critical if you're making decisions about humans. There's no single number. There's a menu, which is why the field talks about model cards and evaluation suites now. The honest answer is, here's how it did on 8 different tests. Pick the one that matches your task. 3 takeaways before the quiz. 1. Intrinsic evaluation. Analogies and similarity judgments. Google's Dataset. Fast, cheap, widely reported, and Linzen 2016 showed the scoring rules are shakier than they look. 2. Extrinsic evaluation. Plug embeddings into real tasks. Measure the accuracy on what actually matters. Slower, more expensive, more honest. 3. Embeddings are mirrors of the training text. Gender bias, racial bias, cultural stereotypes, all in the geometry. Good embeddings is task-dependent. And when the task affects people, unbiased matters more than accurate. Quiz 1. What's the difference between intrinsic and extrinsic evaluation? A. Intrinsic uses more data. B. Intrinsic probes the vectors directly with analogies and similarity. Extrinsic plugs them into a real downstream task. C. They're the same. Or D. Extrinsic is always better. B. Intrinsic tests the geometry. Extrinsic tests the usefulness. Intrinsic runs in minutes and reports one number. Extrinsic requires building a real classifier and measuring downstream accuracy. Slower, but honest. And they don't always agree. Good analogy scores don't always mean good sentiment or NER. Quiz 2. What did Linzen 2016 point out? A dataset was too small. B. The scoring excludes the input words. Without that exclusion, accuracy collapses to near zero. C. Analogies don't exist. Or D. Only English works. B. The exclusion hack. When you compute king minus man plus woman, the closest vector is often just king itself. So the standard scoring excludes the input words from the answer candidates. Without that exclusion, the 72% accuracy collapses to about 2%. The whole benchmark's number depends on this implementation detail, which makes it a much weaker signal than it looks. Quiz 3. Why do embeddings absorb bias? A. They were designed to be biased. B. They're mirrors of the training text. If the internet contains bias, the geometry captures it. C. Only word to a vec. Or D. No bias. B. Mirrors. Bolukbasi et al. 2016 showed man is to programmer as woman is to homemaker in Google News word to vec vectors. Every gender stereotype in the training text ended up as a consistent direction in the geometry. Same for race. When those embeddings feed resume screeners or loan applications or search engines, real people get harmed, which is why the modern answer to good embeddings has to include bias audits, not just accuracy numbers. Back to the puzzle. Embeddings are not a single thing you evaluate with a single number. They're geometry. They have properties. Some properties are useful, some are dangerous, and figuring out which is which depends on what you're building. Next video, Lecture 5 recap. All 10 videos condensed. Then the bridge to Lecture 6, where embeddings stop being the endpoint and start being the input to deep networks. Next time, Lecture 5 recap. 10 videos, 9 one-line theses, and the bridge to Lecture 6, where we take embeddings and stack them into deep networks, RNNs, LSTMs, transformers, GPT, the whole modern era. Hit subscribe.